Alright, so now let's talk about hemoglobin. And keep in mind, hemoglobin is an allosteric protein, but the first thing I want to mention is this prosthetic group, prosthetic heme group. This is really made out of two parts. This is made out of iron in the +2 oxidation state, and then a really long organic compound known as protoporphyrin. So some things we could say, obviously, about iron being the +2 oxidation state. That makes sense because oxygen has a -2 charge to it. But protoporphyrin, it's a planar molecule. It's made up of 4 pyrrolidine or pyrrole rings, and again, I don't have any pictures of it. And then also methionine bridges that are going to connect it to each other. So it's planar, it's conjugated, and at the center of it we have the iron in the +2 oxidation state. Now I'm going to make the assumption you already know that iron is going to bind to oxygen. But because it's planar, because it's flat, there's two sides to this. If we would imagine, just really looking at it here from a side angle view here, we see that this is what we have here. So there's a positive charge on this end and a positive charge on that end. That's where we get that from. Presumably the empty, I guess that'd be an empty p orbital perhaps. I'm not really sure. I need to remind myself on my organic chemistry, I guess, especially with transition metals. But anyways, we can have binding on the top or on the back side of these. And so these are known as the 5th and 6th coordination sites. This is the 5th coordination site, and I'm going to switch colors to draw this 6th coordination site. This would be the 6th coordination site. Think of it as the top and the bottom. So for the 5th, there is attached to this is a histidine molecule, and the imidazole ring of the histidine, which is connected to the rest of the molecule. Remember that hemoglobin is a allosteric protein; it's quaternary level structure there. This is going to kind of pull down on it to create this change in conformation. So that's what histidine does. So the histidine imidazole group here, if we were just to imagine this as the I'm just going to draw it as his here, is going to kind of grab this iron and pull down on him. This is going to cause, so even though it's a conjugated planar flat molecule, the iron has 4 groups attached to it, so it's a lot more flexible than the rest of the parts of the molecule, and so it's going to be pulled down. And this puckering that's happening here, that's going to, when that histidine is there, that's what's going to hold it down into the T state or the deoxy state. It's going to have a 0.4 angstrom angle difference between those two here, and that's what keeps it in the T or the deoxy hemoglobin state. This is otherwise known as the proximal histidine. Okay, so what's usually at the 6th coordination site is going to be one of two things. And I'm going to switch colors, I guess, to really reiterate these. In the deoxygenated state, we have another histidine molecule with his imidazole group the same way. And what this is going to be doing is this is going to block access to the iron. So make sure that iron stays in the +2 oxidation state, and nothing else is going to come in and mess with it and convert it to the 3 oxidation state. That's what we would see up here at the top. Now another thing that we have, and this is obviously the more important one to talk about, would be that this is the site where we have O2 binding. And when oxygen binds, the pull that was on this histidine gets, if you can imagine O2 grabbing this iron molecule and pulling it out, it becomes more even, and that induces a conformational change, in which case the binding of iron acts as a positive effector molecule. Okay, so one thing else to mention is that this histidine here that's located at the 6th coordination site is sometimes called the distal histidine. Obviously, hemoglobin is also an allosteric protein, and so if it's an allosteric protein, we have some things that we need to say about this. The models that we use is actually considered a combined model. And what I mean by saying that is that it's part of the sequential model and also part of the concerted model. The other things we need to say is the subunits of it and the way that we connect those subunits and the functions of each of those. So there's 2 parts of this. The alpha subunits, and then there's the beta subunits, okay? And both of these guys are very structurally and arguably I think that it shows a sign of homology, having a similar to myoglobin, which, if you think about that, that should hopefully give you some reminiscence of that. These also tend to exist in their dimerized form with each other. So when an alpha and when a beta subunit come together, we can sometimes say it's an alpha 1, alpha 2, alpha 1, beta alpha 2, beta 2 subunit dimer. So they can form dimers together existing in this quaternary level protein such as hemoglobin. But now I really wanted to talk about the combined model. I should have said combined model. I don't know why I just wrote combined there. That explains this. So just like we have before, there is a T-state for this. We've clearly defined this, a T-state and an R-state for this, and it exists in equilibrium. The T-state obviously being the deoxyhemoglobin, and then the R-state being the oxygenated form. So what is the mechanism that you're probably wondering, or at least I'm wondering, what the mechanism is that controls the equilibrium shift between right and left? Well, there's a lot of things that come into play with this. I'm not going to talk about effector molecules so much as I am going to talk about what we kind of previously mentioned with the heme group, with just the actual processes of things that are binding. So I'm going to say we have effector molecules, which we'll go into detail later, but this is an outline. There's the effects of O2 binding. And then lastly, there's the actual combined models. I guess I should have mentioned the exceptions, I guess would be what I'm trying to say here. So for the combined, we have the sequential and the concerted. Yeah, I know my handwriting's bad, but that's not superbly important. So for effector molecules, this is just to name a few. There's a lot of other ones, but protons, for example, acidic conditions is one. Carbon dioxide is one. There's a new thing that we're going to talk about called 2,3-BPG. We'll explain what that these three things later. And then there's the actual process of oxygen binding. And then what I mean by saying the exceptions is just that. So when oxygen binds, it generally, for the most part, displays positive cooperativity. However, this positive cooperativity is not intrinsically all concerted or all sequential. So let's talk about what I mean by that with the exceptions. So say, for example, in our quaternary level hemoglobin, 3 out of the 4 subunits are oxygen. This means that it's going to be predominantly in the R state, which is the oxygenated state anyways. And it's going to have, for that 4th hemoglobin, for the 4th subunit, so I'm just going to say the 4th is going to be 20 times stronger. 20 times, it's going to have a 20 times stronger affinity for oxygen at its active site. Well, I mean, and that's not an enzyme, but at the binding site, sorry, than that of just, say, it by itself. And that's what I meant whenever I mentioned that we have positive cooperativity, is that if you have, in ignoring the description here, or ignoring the explanation, the description is that the more oxygen you have, the higher affinity you have. More O2 binding equals more affinity for the entire quaternary level structure, for the molecule as a whole. More affinity. So if we have this, we have say 3 out of the 4 occupied, we have 20% stronger. But let's see what would happen if we took the opposite. If we say that only 1 out of the 4 subunits in our allosteric protein had oxygen. Well, and this is where we say that it's a combined model, because this is kind of the exception. This is going to be, for the most part, in the T state, right? The others are going to be T. So we could also say, well, this is an isolated event, right? Because it's not having any effects for this. And so even though this is in the T state, the majority of it is in the T state, it still has a stronger affinity for oxygen than, say, that of the completely deoxygenated molecule. So that's what that's about.